Let us discuss the next concept, that is phase shift of components in star delta connected transformer backs. So here we are going to discuss the angle, the shift which is going to occur to the symmetrical component while passing from primary of the circuit to the secondary of the circuit in the case of a three-phase transformer or bank of three identical single-phase transformers which are connected to form a three-phase transformer. So here we are going to refresh some of the concept, that is the phase shift in a single-phase transformer. There is going to be a shift which is occurring between the primary and the secondary of the voltage, and the current is depending upon the primary and the secondary winding, the way of the connection which you are going to do it. The polarity of the winding which is going to determine the phase shift, that is here we can see to that it is mainly depending upon the Lenz law, that is applying the Lenz law and right hand grip rule for the configuration. So here H1 is indicate the high voltage side, and X means X1 and H2 are indicate for the high voltage side, X1 and X2 indicate for the low voltage side. So here we can deduce that I2 will be which is in phase with the I1, and the terminals of H1 and X1 are positive at the same time with respect to the S2 and the X2. So dot is placed at the terminals having the same polarity. Okay, in opposite polarity, the other side the dot will be coming here. So that is nothing but the direction of current I2 is reversed while the direction of the I1 remains same. So in that case, we can see to that I2 will be 180 degree out of the phase with respect to the I1, or it may be in phase with the I2. Okay, if that is there is no phase shift. So from this what we can understand is that the primary and the secondary currents are either in phase or 120 degree out of the phase depending upon the direction of the positive for the flow of the current which you are going to assuming that. Okay, so similarly the primary and the secondary voltage may be in the phase or 120 degree out of the phase with respect to the primary. Thus the polarity of the winding which is going to determine the phase shift. So with this background we are going to understand the phase shift between the case of star to delta, delta to delta, and star delta and delta to the star, different way of the connections. So here winding of the delta to delta or star to star, the transformer are connected so that the phase shift for both the currents and the voltage is either 0 degree or 180 degree out of the phase. So whereas in case of star to delta or delta to star transformer, the winding connections can be made so that the phase shift between the transformer winding is equal to n into 30 degree, where n is depending upon the number of the whole number called hour number. Okay. So in many years, in the absence of the standard transformers for the manufacturing with a different windings connection to get different phase shift. So in the year of 1988, ANSI, that is nothing but American National Standard Institute, established the standard for these connections. So according to this, so they have made a regulation that high voltage side should lead the low voltage side by 30 degree with respect to delta to star or star to delta connection. Let us consider that the star to delta transformer here, the high voltage side which is marked as H1, S2 and ST with respect to the phase A, B and C, and the low voltage side which is considered the X1, X2 and the X3. So AN is nothing but here the neutral across the star connected side of the transformer. So V means VAN is always in phase with VAB. Okay. So consider that. Okay. The equation that we know, whereas in case of the positive sequence of the component, so we know that the VB1 which is going to lag with respect to the VA1, and similarly VC1 which is going to lag with respect to the VA1 at an angle of 240 degree. So according to this, means according to that ANSI, American National Standard Institute, for the designation terminals, the voltage of HV side, that is H1, should lead the X1, okay, by 30 degrees. Similarly for S2 should lead with respect to the X2 by 30, and similarly for S3. So let us see to that. So how we can draw this, means the positive and the negative sequence of the voltage with respect to the primary and the secondary side, or high voltage side with the low voltage side. Okay. So if you look at that, it is how we are drawn. It is a measure with all the phases. Okay. Let us see. Let us understand that. So VA1, okay, this VA1 and VAB1 which are in phase. Okay. So whatever the angle which is made by VA1, it is same as the VAB1. Okay. So let us draw this once. Okay. So this is nothing but, first we are drawing for the high voltage side. This is nothing but VA1. Okay. Means capital A1 is for the high voltage side. So the angle which is made by BB is 120 with respect to that. Okay. This is time for VB1. Okay. VB1. Similarly, there should be 120 degree with respect to this. Okay. So this is nothing but VC1. Okay. This is also 120 degree. Fine. So what will happens? This is nothing but the terminal which you can consider it is A1. Okay. So this is nothing but B1 terminal. B1. So this is C1. Okay. Join these things. Okay. From here to here, and from here to here, and from here to here. Okay. What is the common between these things? Okay. What is the common between here? Okay. Between V, this is the terminal A1, B1. That's so what will happen? This is nothing but V A B1. Okay. This is nothing but VAB1. Similarly, this is a VBC1. Okay, this is VBC. Similarly, this is VCA1. Okay. So 1 is stand for the positive sequence component. Okay. Then coming to that, the right hand side, that is nothing but delta connected side. Okay, voltage side of the circuit. Okay, which we are considering that. So I told that this is a VA1. What is the angle which is made? It is same as the, okay, it is the same as, okay, it is same as the VAB1. Okay, VAB1. Next, what is the angle which is made by, it is VB1. Okay, this is VB1. VB1, which is same as, okay, so what is the angle which is made by VB1, which is same as VBC1. Okay, So here in this way which we need to write. Okay, so means we are writing here. So this is nothing but V B C. Okay, and similarly for BC1, okay, which is VC1 is same as the VCA1. Okay, this is nothing but which is same as VCA1. Okay, so how we need to write the star connected values, okay, at this point. So once again I am writing at this point, this is nothing but VAB1. Okay, so simply draw a star connected network inside of this figure. Okay, so what is a common terminal between these two? Okay, what is a common here? So this is VBC1. Okay, VBC1, and this is the VAB1. So this will become VB1. So here it is VCA1 and this is a VBC1. So here this is the C1 is the common. Okay, and here the A1. Okay, so what will happens? The middle is a neutral. So what will happen? This is what we can write it as. This is VA1. Similarly, this is VB1. Okay, and similarly, this is VC1. So if you look at that, what is the angle which is made? Okay, so this is VA1, capital VA1. This is the small VA1. So from this, what we can see is the high voltage side should lead with respect to the low voltage side. So if you look at that, VA1 which is going to be lead with respect to the small VA1 by at an angle of 30 degree. Okay, so here if you draw that VA1 here, so this is nothing but capital VA1. So whatever the angle which is made here, it is 30 degree. Okay, so this is 30 degree. So from this what we can see is, so this is VA1, capital VA1 is advanced by small VA1 at an angle of 30 degree. So this is obeyed by, means positive sequence component which is obeyed by the ANSI standard. Similarly for the negative sequence component, okay, let us draw this. So how we need to draw it for? Okay, so let's see, this is VA2. I told that VA2. Okay, VA2. So here next we should write this is VB2 and this is VC2. But here because this is the negative sequence component, then that's why we should write this is VC2. Okay, then this is VB2. Okay, so then this should be VB2. Okay, so join these things. So from here to here, so from here to here, so from here to here, what we'll get? So this is nothing but A2. Okay, A2. This is C2, and this is B2. Okay. So similarly, what will happens? So between A and the C is nothing but VAC. Okay, VAC, VAC2. So between C and the B is nothing but VBC2. Okay, between A and the B is nothing but VAB2. Okay, VAB2. So next, so here we told that, so this is the same as, means whatever the angle which is made by VA2 is same as the VAB2. Okay, let us draw this. So what is that? What is the angle which is made by VA2 is same as the VA, okay, B2. Okay, and And the similarly, what is the angle which is made by VC2? Okay, VC2 is same as the VCA2. Okay, here this is nothing but VCA2. Similarly, for the VB2 is same as VBC2. Okay, so this is VBC2. Okay, just make a common point. Okay, draw a star between these two. Okay, what is the common here between VAB and the VBC? Is nothing but this is B. Okay, so this will become B, so this will become A, and similarly this will become C. Okay, so if you look at that, VA2 capital, okay, capital VA2. Okay, so here just I think we have to write this, because this is nothing but VC. Okay, this is VC2 and this is VB2. Okay, and this is VA2. Okay, so if you look at that, what is the angle between VA2, capital VA2 and the small VA2? Okay, if we represent this here, the angle which is made, this is V capital A2, here it is 30 degree. Okay, 30 degree the angle. So it means that the high voltage side which is going to lead with respect to the low voltage side at an angle of 30 degree. So it means that capital VA2 which is lags with respect to small VA2 by at an angle of 30 degree. So that is the meaning of it. So let's consider that we know that the line to line for the star connected winding to the rated to the line voltage of the delta kind, which is equal to that, we can write it as it is a root 3 times of N1 by N2, means it is a root 3 times of the ratio of the N1 by N2. Okay, so we will get capital VA1 is equal to root 3 times of the ratio of the N1 and N2 with respect to the angle of small VA1 at an angle of 30 degree, and for the capital VA2 which is equal to root 3 times of N1 by N2 of at an angle of minus 30 degree. So it is meaning that this is a plus degree and this is the minus 30 degree. So in the case of negative sequence line voltage, it seems that it is going to be violating the ANS standard. So it means that according to the ANS standard says that high voltage should lead the low voltage side by 30 degree, but in this case, so this is going to be lag. But however, it is not the violation, because ANSI is particular only about the positive sequence component. Let us discuss power in terms of symmetrical components. So in a symmetrical components of the current and the voltages are known, then the power in the three-phase circuit can be computed directly from these components. That is, so that we know that the complex power which is going to flow in the power circuit, which is given as S is equal to P plus JQ. So, okay, so apparent power is equal to active and the reactive power, and with respect to what is the voltage and the current. Okay, so here S is nothing but total complex power, and the P is nothing but active and the Q is reactive. So here star indicates that it is a conjugate. So this can be written as P is equal to J plus KQ. Just we are rearranging this equation and writing in the matrix form. Okay, it is VAB, VA, VB and the VC. This is IA, IB and the IC. Okay, 3 cross means row and the column matrix. If you multiply, we will get the row matrix. Okay, so call this equation is 1. And VAB, VB and VC can be written as it is a transpose of the matrix. Convert this is a row into a column matrix. Okay, so and consider that. So already we know that So VAB can be written as, so this is one of the matrix, 1 1 1 1 A square A and 1 A square, VA0 VA1 and VA2. So if you wanted to calculate the line current, line voltages by using the phase component, means phase sequence component. Okay, so already we know that this equation VABC can be written as 1 1 1 1 A square A 1 A square into VA0 VA1 and VA2. So here it is a complete transpose of the matrix. Okay, so this can be written as VA0 VA1 VA2, just taking to the left means just rearranging these things, okay, onto the right hand side. And here you can see that when you do a transpose of the matrix, rows will convert it into a column matrix. So this is a 3 into 3 cross matrix. So what will happen if you convert that? First row, okay, this will become first column. Next row, this will become to column. Okay, you can see here, observe 1 A square A. So this 1 A square A. It means that, so this is going to be in first row, okay, and the first column, second row and the second column, third row, third column. Okay, so this is what, so third row, okay, third row, this is nothing but 1 A square. So this is going to be third column, 1 A square. Okay, so this is called, this is the second equation. So since we know that, so A into B transpose can be written as A transpose and the B transpose. So that is nothing but IA, IB and IC of the conjugate of the matrix can be written as same way. So this is how we have written for the values of the line current by using the symmetrical component. So this can be written as 1 1 1 1 A square A 1 A square. This is IA0 I1 and IA2. So this is a complete transpose of the matrix. So we know that, so A into B transpose of the matrix can be written as A transpose and the B transpose. Okay, so this is again same thing. So write this. So means we are taking this transpose of the matrix into the each of the matrix. This is also transpose of the matrix. This is also transpose of the matrix. So we know that A transpose can be written as A square. So A square of the transpose of the matrix will become, so A cube is, this will become A. Okay, means A square of the transpose of the matrix will become A. So by using these things we can write it as, just rearranging this, okay, I, B and IC. So here we are transposing of this matrix. Okay, so what will happen means the conjugate of the matrix will become 1 1 1 1 A square A. Okay, so this is the conjugate. So this is a, what is that? This is a indicate there's a conjugate of the matrix. Okay, so A square conjugate of the matrix will become A. Okay, so here this is A, so this will become A conjugate of the matrix will become A square. Just we are writing these values in the matrix. Okay, so call this is the equation 3. Then substituting this equation 1 and 2 in equation 3 we will get, okay, means we are writing that P plus JQ. So here, so this is nothing but VA0 VA1 VA2 of the transpose of the matrix with respect to 1 1 1 1 A square A. So this is nothing but, this is the value of the VA, VB and the VC. Okay, so that is the value of the transpose of the matrix, and this is for the IA, IB and the IC values. So this is the 1 1 1 1 A square 1 A square A. So this is the IA0 I1 IA2 of the conjugate of the matrix. Okay, by after doing the simplification what we will get, this is VA0 VA1 and VA2. Okay, so transpose of this matrix will become a row, column matrix can be converted into a row matrix. Okay, so while doing a multiplying of this matrix, okay, we will get only the diagonal element. Okay, and this is the value of the current. So multiplying this, what we will get, so S is equal to P plus JQ. So will become 3 into VA0 IA0 of the conjugate plus VA1 I1 of the conjugate of the matrix and VA2 IA2 conjugate of the matrix. So this is nothing but the symmetrical component of the current and the voltages. If you are known, then the power consumed by the three-phase circuit can be computed directly from these components. Means you should know, if you know that the value of these component values, so directly we can able to calculate of what is the total power which is consumed by the network.